Labrīt, godātie viesi, godātie draugi, kolēģi, godātais rektori. Priecājos jūs sveikt 10. kognitīvo zinātņu simpozijā Telpiskās kognīcijas perspektīvas. Dear honored guests, dear friends and colleagues, dear Rector of the University, I'm pleased and welcome to see you all in the 10th International Symposium of Cognition, Logic and Communication. This time entitled Perspectives on Spatial Cognition. Let me be brief. On behalf of the Center for Cognitive Sciences Semantics, University of Latvia, and also on behalf of co-organizers of this conference, Michael Glansberg from Northwestern and Peter Svanonius from Tromsø, Norway. Unfortunately, they are not able to be present today, but on behalf of our organization and program committees, let me wish you a great conference, a lot of discussions, a lot of inspiration in the next 2 days. I hope you will not forget this event. And I'm honored to give the floor to the Rector of the University of Latvia, Professor Mārtis Auziņš.
Good morning, dear colleagues, dear guests, ladies and gentlemen. I am really happy to welcome all of you to the University of Latvia for the opening of 10th conference about cognition science, and the particular title of conference I was expecting to see on the screen, but it's Perspectives of Spatial Cognition. Probably many of you are for the first time in Latvia and for the first time at the University of Latvia, and I think it will be appropriate if I will give you a very brief introduction to the University of Latvia. Currently, University of Latvia is the largest university in our country. It's the only one classical type university. It means that we have almost all subject areas represented at our university, except we have very little engineering. It was kind of historical development of the university that at some point engineering departments were separated at the Technical University of Riga. But otherwise, we are covering science, social sciences, humanities, medicine, teachers training, and in humanities and social sciences, in some sense, we have exceptional position because in humanities, almost all the research which is carried out in Latvia is concentrated at the University of Latvia. The University of Latvia is not very old. Foundation date of University of Latvia is 1919. We are celebrating 95th anniversary this year, but actually, again, it's kind of tricky historical development because in this building, university was before the University of Latvia was founded. It was German Technical University. But right after the First World War, there was sentiment for independence, for national development, and then when German university was transformed into the University of Latvia, it was decided, very untypical for Europe, that we are not counting previous histories, that we are deciding that we are starting with national university and national research center from zero. This is why we are only 95 years old, despite that the university was in this building more than 150 years. We have around 16,000 students. Again, for European scale, it's kind of a medium-sized university. But when I'm willing to impress my guests, I'm saying, look, it's almost 1% of current population of Latvia. Probably it tells something about country in general, that we are a small country and we have only 2 million inhabitants currently in Latvia, but probably it tells also what kind of role we are playing in Latvia in our society. We are a research university. Together with our research institutes, we are contributing very significantly to the research output of the country. It's not easy to measure in quantitative way research output, but there is some means. And if, for example, we are counting publications in the Web of Science journals, then we are contributing more than 50% of all the research output which is coming from Latvia. Another way is to count PhD students, how many PhD degrees are awarded each year. Again, from this parameter, we are awarding more than 50% of all the PhDs which are coming from our country. So this is what kind of university we are in Latvia, and we are very happy to hold this conference. And when I'm looking at the list of authors and contributors to the conference, even if I am coming from physics and not specialist in your subject area, I am seeing that there's really constellation of stars present in this conference. This is actually very typical when Jurgis Šķilters is organizing conferences. This is why we are really happy to welcome all of you here. I'm sure that in this lecture room and in parallel sessions, you will have very many very important talks. But maybe a little bit untypically, I will wish you many long coffee breaks. Because especially in your science, I believe that personal contacts and personal discussions are extremely important. And for that you need a little bit free time from official talks and official gatherings. And I hope that you will have enough time for all these direct conversations and direct interactions. I hope that as a result, maybe some new ideas and maybe some new projects will start. And if the University of Latvia will be part of these new projects, I will be more than happy. And then from my viewpoint, the main goal of the conference will be reached. New ideas, new contacts, new research, and probably new important results for next conference and next meetings. Hopefully weather will be nice. In the Baltic states and in the Baltics we are very close to sea, and you never know, but hopefully it will be nice because you are right in the city center, and there's excellent opportunity to see Old Riga as well. So I wish you a very successful conference, very many new ideas, and success for your future research. Thank you.
Thank you so much, Professor Auziņš. So, and now I would like to give the floor to David Udall, Professor of Psychology and Education at Northwestern University, United States, Principal Investigator at Multidisciplinary Program in Education Sciences, and Director of Psychology and Director of Graduate Studies at Northwestern University. We'll introduce a talk by Professor Gentner.
Thank you, Jurgis, and other members of the university for welcoming us to your beautiful city and beautiful university, and I think it's going to be a wonderful 2 days. Well, it's my great pleasure to introduce my friend and colleague, Dedri Gentner, Professor of Psychology and of Education and Director of the Cognitive Science Program at Northwestern. Dedri demonstrates a remarkable degree of both breadth and depth in her work. As you'll hear, the breadth is truly extraordinary, ranging from analysis of the metaphors that Kepler used in making his discoveries several hundred years ago to the relation of time and space in Chinese and English. And yet, despite the incredible breadth, there's also an intense depth in that she studies all of these processes in terms of what she considers, because it is, a fundamental human ability, and that's analogy and comparison. And you'll hear that her work on analogy and comparison is based on very clear cognitive and computational models that get at the mechanism of how analogy works, and, as you'll hear, makes us smart as humans. She's also equally at home working with children or with adults, and in fact is one of the leaders in integrating the developmental perspective into cognitive science and using development as one tool for studying cognitive science and cognitive change. So her awards and honors are so many that to list them would take away from her wonderful talk, but she really is one of the founders of the modern interdisciplinary study of cognitive science. She's never content with simple answers and always focuses on cognitive mechanism. So without any further ado, I welcome Dedri Gentner.
Thank you very much, David. Let's see, can you all hear me, or should I bring this down a bit? If we make it a bit lower. Okay, how's that? So let me begin by thanking Jurgis Skilters and the other organizers of the conference and President Auzinski, I hope I pronounced that correctly, and the University of Latvia. It's great to be here. I feel really honored to be kind of part of this meeting and part of the contribution to cognitive science in Latvia. So without further ado, let me introduce the topic of my talk, which is analogy as the key to higher order cognition. What do I mean by analogy? I mean basically similarity based on common relational structure rather than common concrete features. So, for example, a famous historical analogy is the analogy between the atom and the solar system that Rutherford put forward in 1904. Now, this is not, of course, current model in physics, but historically it was very important. It allowed a way of conceiving of the atom as an object with a large, massive central item and smaller items that were attracted to it but revolved around it. So it provided a model for how one could think about the atom. And notice that this is just about the relations among the central object and the peripheral objects. It's not a concrete model. You don't think of the nucleus as a hot, yellow, gaseous object like the sun. It's all about the relationships among the objects in the system. That's a typical analogy. So my claim in this talk is that this kind of relational reasoning is central in higher order cognition. It's what allows us humans to be as powerful as we are in thinking about abstract topics like mathematics and so on. There's evidence that this is the key difference. This ability to see relational similarity is the key difference between ourselves and other species. And it plays an essential role in many different cognitive phenomena. So these are the specific claims I want to make. Relational reasoning is central in higher order cognition. I'll also note that for children, acquiring this kind of insight is challenging. So developmentally, we can see some bumps along the road before children become as proficient as adults. I'll also describe a structure mapping process, which is the mechanism by which we carry out these processes. And I want to suggest that the same structure mapping process applies to children and adults and across different topics, perception and higher order conceptual topics and so on. So it's very, the same process really does a lot of work for us cognitively. So this is basically the encapsulated argument. This process of analogical comparison, you can see it in analogy and metaphor, but also in categorization, in learning and reasoning, scientific discovery, perceptual similarity, and so on. So I will not talk about every one of these topics, but I'll try to make examples that hopefully will give the flavor for this idea. So what does all this have to do with space? This is a conference about spatial cognition, and the reason that I think analogy makes an interesting topic in terms of spatial cognition is that space has a particularly special relation with analogical processing. First of all, spatial analogies are extremely common. Whether you're talking about a Venn diagram for math and logic, where you intersect perhaps complex categories in terms of physical spatial intersections, or whether you think about ordinary conversation where people refer to communicating an idea as though they were passing an object back and forth in space. Your argument goes too far. I'll lay it out step by step. We're talking about something very abstract, but we use spatial language to do it. So Spatial analogies are common, and I speculate that this is because space is a beautiful domain. It's a domain that has, first of all, we're all very familiar with it. It's very well learned, but more importantly, it's a kind of beautiful domain. We have, for example, if in Cartesian coordinates, if you go over one and up one, you will always get to the same place as if you go up and then over. It has lovely sort of regular structure, and this makes it, I think, a powerful domain to use to make inferences and to structure other domains that are less clear to us. So you'll see in this talk that many of the examples will involve spatial analogies. So what I'm going to do is talk about the structure mapping idea, of how these analogical comparisons are made, then give some examples of different ways in which this shows up cognitively, then talk about how this kind of work, this kind of process leads to learning, and then back this up with empirical studies of children and adults. So, claim one, we learn relational patterns by comparing exemplars, and this happens by a structure mapping process. By structure mapping, I mean a process that, first of all, involves representations, mental representations, that have relational structure. So let me describe this representation that you see. There will be objects of some kind, but then there are relations between the objects and relations between the relations. And I'm going to make the assumption, which I hope many of you will share, that we humans very easily store these kinds of structures and can use them in thinking. So given that you have this kind of representation, when we compare things, we are comparing these, we have two representations, the two things we're comparing, and the process of structure mapping basically aligns the relational structure in the two representations according to some implicit constraints. We're not aware of doing this, but nonetheless, if you show people analogies and watch what they do, or run experiments of various kinds, you can see that we like to find one-to-one correspondences between the items in one set and the items in the other. We want there to be parallel structure, so if two relations match, then their arguments should also match. And we like systematicity, which means we like connected systems of relations rather than isolated coincidences. So matching in the analogical matching is not just about finding lots of matches, it's about finding a connected system. We prefer to find connected systems. This is one of the reasons it's a good process to use if you want people to learn something, because it will tend to lead to finding common systems such as causal systems. Okay, so let's look at an example. If I give an example to my class of students, like this, Walcorp sold off best tires. Likewise, Martha divorced George. And I asked the class, what do these have in common? What is this analogy about? The class will say something like, they all write out their answer, and pretty much they come to the conclusion that these two statements are both about someone getting rid of something that they no longer want. Martha got rid of George, Walcorp got rid of best tires, even though those are very different, right? Martha's not much like Walcorp, but you can still see the same relation as holding. So that's not hard, right? People can do that. Now you see if people can make a new inference. You say Walcorp sold off best tires and bought a more profitable tire company. Likewise, Martha divorced George and you ask for an inference. Maybe you've all formed an inference by now. What the class generally says is something like, she married a richer man, maybe a more handsome man, you know. What they don't say is, bought a tire company, right? So this is fairly miraculous when you think about it. Just very readily, without any effort, they translate buying a tire company into what would structurally correspond to it if what you had just done is divorce your husband. If you get a new husband, not it's not a concrete match of tire to tire. It's a match of this, the thing that has the same relation to getting rid of a husband is getting a new husband. So this is something we are really good at, we humans. So just let me put this, say this same set of ideas a little more abstractly. When we compare two things, the common structure becomes obvious, becomes evident, it sort of emerges. So you compare these two examples and you get they got rid of something. When we compare two things, new inferences become kind of obvious and spontaneous very often. So the idea that she got a new husband is fairly effortless for us, as we don't have to strain to find it. And one more thing that I'll tell you more about later is when you compare two things, if there are differences between them that play the same role in the two structures, then those will sort of be highlighted. They'll emerge as very obvious and noticeable. That can be very useful. So I'll return to that later in the talk. So to summarize, when you do a structure mapping between two relations, you reveal commonalities which might give rise to abstractions. You can project new inferences. You highlight differences, and you can, because these kinds of processes favor connected information, they also support extended mappings. I'm just going to give you the 1-minute version of the computational model that Ken Forbes and others are building or have built. So this will be very quick. If you would like a more detailed version, please ask me after the talk. But what I like about the model is it's very stupid to begin with. You don't have to know the answer in advance. Just as, you know, the class doesn't know the answer when I say Martha divorced George and Walcorp sold off Best Tire. They don't know until they see it. Well, what is going to be the common structure? So it begins with two representations, and it makes every possible match, many of which are completely silly in the end, every possible identity match. That's stage one. Stage two, it pulls this nest of things apart into little pieces that are structurally consistent. We call that kernel, so they have to be one-to-one correspondence and parallel connectivity. Stage three, it tries to put those kernels together into the largest possible match, and it almost always gets the best match, although if you examine it, it doesn't always, just as we humans don't always. And then it rates the match for how good it is, meaning how deep, how structurally consistent, and it'll always be structurally consistent, but how deep it is and how many kernels it has, how many matches. And finally, if there's an inference that can be made, because there's a part of one system that's connected but not yet present in the other, it'll spontaneously make the inference. So, I could say much more, but let's leave it at that. The things I like about this simulation are it's initially symmetric, so you don't have to pick which one is which thing you're using as the source domain. You don't have to know the answer in advance, as you do some other systems. You do have to guess the answer in advance. You don't have to guess it here. That's really important for capturing learning. And you get deep mappings. I think that's, again, fits the human data. And because you don't have to know anything in advance, it captures the fact that comparison can reveal new insights that you didn't even glimpse until you started comparing. I'll show you an example like that from kids. Okay, so the pervasive role of analogical mapping. So I'm just going to give you a bunch of examples from different arenas that in which you can sort of see these processes. So this is the sort of, grand claim. So scientific reasoning, we've already talked about, the Rutherford example, and down below you see a baleen whale and a hummingbird, and the correspondence between all of their skeletal parts is sort of an astonishing set of basically one-to-one mappings. This is an example used in education. Again, a nice analogy where you're trying to get across to students that if you keep putting carbon dioxide into the atmosphere and not taking it out, then it's going to keep increasing. And as I'm sure you know, this idea can be hard to communicate. So the analogy is a bathtub. If you have the water coming in and the water draining out, and if the inflow is greater than the outflow, the amount will keep rising and the bathtub will overflow and so on. This kind of analogy can make the atmospheric carbon dioxide easier to understand. Then in metaphor, literary metaphor, we see very often these kinds of relational matches. Here's a Virginia Woolf example. She allowed life to waste like a tap left running. Kind of a evocative example. Perceptual similarity. Here's a really simple triad in which I ask, if you look at the top figure, which one of the bottom figures is more like the top figure? Would anyone like to pick this one? How about this one? I think most of you are going on the right, and that's reassuring. This basically is evidence that I'm dealing with an audience of humans, because if you were baboons, you would find this really difficult. And this is where I mentioned earlier that we humans are really good at this compared to other species. So this kind of relational matching, where you have an identical pair here, and you ask whether the subject would find another identical pair similar versus a pair that's different, this seems so trivial to us, we can't even imagine it could be a problem. Someone recently set out, Joël Fagot and Roger Thompson, set out to teach baboons to do this. And after 21,000 trials, 6 out of the 29 baboons had succeeded. So that's a fairly dramatic contrast. Now, baboons are monkeys. Chimpanzees, which are like us, are apes, do somewhat better, but it's still something like 300 trials. So, this is something we humans are incredibly good at compared even to other primates. So now let's ask about young humans. It turns out this is, for 4-year-olds, this is not a problem. They can do this problem, basically as soon as you start showing it to them. But 2.5 and 3-year-olds do not initially see it. It's not obvious to them. And then we can do some things that make it more obvious. We have a whole line of experiments on how you make it obvious to 2.5 and 3-year-olds. But even for humans, there's some learning to be done to unlock our full analogical potential. Here's another example of the pervasiveness of analogy. In ordinary life, without even paying any attention, we use these little analogies in sort of normal conversation. And this is an observation by Doug Hofstadter of what he calls the Me Too phenomenon. So the one person says, I'm going to pay for my hamburger. And the other one says, me too. But that person had a Coke, right? But, it would be bizarre to say, what do you mean? You had a Coke and I had a hamburger. That's totally different. We just immediately translate it into pay for the thing that you bought, right, that you ate. And an even better example, I think, is a woman says, my mother's always calling me by my sister's name, Carol. And the man says, mine too. Well, he's probably not called Carol, and it's probably not his sister's name. But again, the appropriate mapping is made, and it's something we don't even recognize as a challenge. So that's the end of the pervasive role of analogical mapping, of how it pervades everything from education to scientific discovery to ordinary conversation. And now let's ask how. How does this work? How do we learn from analogy? And here's where we'll get into some empirical work. So the first study is on how comparison promotes relational learning in children. This is done by Stella Christie. So what we decided to do was teach children new spatial relations that we were sure they didn't have. These are 3 and 4-year-olds. And they don't have a name for small thing above large thing, otherwise identical. In fact, I bet there's no human language that has a word for that. Some of the other things, like the 2 pigs, we could call that symmetry. We adults would have a name for it, but at 3 and 4, they don't have this name. Other people have looked at that issue. So here's how we do the study. We show our 3-year-olds. I'm just going to tell you about the 3s. We show the 3-year-olds one of these pictures, and we can say, this is a toma. Kids love learning word meaning, so it's a good way to get them to be interested. This is a toma. Which one of these is also a toma? So they have to choose between the two bottom examples. Now, again, I'm sort of guessing that you would probably choose the other symmetric pair if you were in this experiment, but that's not what we expect the kids to do, because the kids are going to be very, very attracted to the object match. For children, object matches are very salient, very obvious, and they don't have a very strong relational vocabulary yet, internal vocabulary. So we thought this would be challenging, and it is. It's extremely challenging. 3-year-olds, basically 98% of the time, choose the object match. They really don't see the relational match. So that's finding number one. And now, what happens if we give them 2 examples and let them compare? Will that make the relational match emerge? Remember, the claim is that if you see 2 things and you compare them, then the common structure will emerge even if you didn't know it in advance. Now, it's not always going to work, but it very often does. If you have parts of the fragments of the structure in each of them and you put them together, the whole thing may emerge. So we say, this is a toma, and then we put down another example, and this is also a toma. Can you see why they're both tomas? And that's to make sure the kids compare them. By the way, they often don't say anything. Sometimes they do, but we just want them to take a moment. Then we ask them the same question, which of these is a toma? And now what you find is 57% will choose the relational match. So it's 2% if they see 1 item, it's 57% if they see 2. It's a factor of about 25 times more relational responding. So this just shows you the same finding in a graph. The 3-year-olds are on the left. The blue line is when they see 1 item, and the red line is when they see 2, and compare them. They're far more likely to choose the relational once they've compared 2 things. And we see the same thing on the right side for 4-year-olds, but they're a little better, of course, more sophisticated. So we can sort of think about this think about it for a moment in terms of categorization. When we tell them that these 2 things are both tomas, they compare them, they derive an abstraction, and now this is this little toma abstraction, which maybe you and I would call symmetry. And then when we ask them to tell us which of 2 new items is a toma, they're basically taking this abstract schema and applying it to the example and asking, does it fit? So this, I think, is what we do with many of our categories. Many categories in human life are relational categories, and we have to apply a relational schema to see if the example fits it. Let me just, before we leave this study, let me just note a challenge that you might want to bring up. You might be saying to yourself, well, the comparison group got 2 examples, and the solo group only got 1. How do we know it isn't just seeing 2 examples? Instead of comparison processing, maybe it's just getting 2 examples. Maybe the kids start off with a couple of hypotheses. Maybe it's about pigs. Maybe it's about pigs. Maybe it's about symmetry. Then when they see the other toma's goldfish, well, that rules out pigs, so now it must be symmetry. That might be possible. So we check that by showing them the examples one at a time, and we don't ask them to compare. In other words, we try to make it hard for the 3-year-olds to actually compare them, but they still get 2 examples. So in this second study, we show the pigs, we say, this is a toma. We take the pigs away, we show the goldfish, and this is a toma. And then we put down the 2 examples, and we say, which one of these is a toma? And if you do that, basically, the children respond as though they only saw 1 example. It's statistically no different from seeing a solo example. They continue to pick the object match. So no light bulb has gone off. Nothing has happened that has changed them from thinking about objects to thinking about relations unless they compare. So the implication is comparison can reveal new relational patterns. common spatial pattern that they really had not seen. Remember, 98% of them miss it when they see one item, but when they see two, they were able to see it and apply it to a new example. So there are many, many examples of comparison promoting relational learning, adults, children, even infants. So I'm going to now turn to another way in which comparison can work, and that is by promoting alignable differences. I mentioned this earlier. When you compare two things, in addition to the common structure becoming more obvious, if there's a difference in between the two things that's related to that common structure, it will also become, it will pop out, it will become salient. So we've asked people, adults and children, many questions like, tell me the difference between a car and a motorcycle. And they will tend to pick two things that play the same role in the two items, like cars have 4 wheels, motorcycles have 2. Or if you say, well, I'll leave it at that. So alignable differences then emerge as a natural outcome of structural alignment. And second point, comparison is faster and easier for high similarity pairs than for low similarity pairs. I'm going to show you evidence for that in a moment. So differences are going to pop out more naturally for high similarity pairs because they align extremely swiftly. They're kind of self-aligning. And when that happens, a difference that is connected to the common structure will become extremely obvious very fast. So let me let you experience this. This is a study that we did with adults. And your job is to, either out loud or just in your mind, but if you want to be good subjects, you might just say it out loud. I'm going to show you a pair of items on the next slide, and if you would please say one difference between them as fast as you can. Let's see, either you are really a very serious and contemplative audience, or you decline to say it out loud. But I'm guessing that many of you have noticed the difference between these two items. I'm seeing a few nods. Yeah. So, thank you. So this one, when you run subjects on this, is very fast, right? Before you even have time to study it, you've noticed black circle versus white circle. All right, now, again, imagine you were in the experiment. I'm going to show you another pair. See how fast the difference emerges for you. Yeah, so of course you can do it, and our subjects will, when we ask them to name a difference, they will type out something like, one of them has a dragon and the other doesn't, or something like that. You know, we can do it, but it doesn't come to you in the same way that a high similarity pair does. These are perfectly alignable, so the difference is sort of realized almost before you try. So basically, if you run pairs that are highly alignable, people are very fast to name a difference. If the pairs are hard to align, people are slow to name a difference. And this is interesting because it's the opposite of what happens in a same-different task. If you're just asking people to say same or different, they're going to be faster for the pair on the bottom. It's extremely quick to say they're different, whereas it's slower to say that the top pair are different from one another. But if you have to say how they're different, the top pair is faster. And I'm not going to go through this graph in detail, but this is basically, on the left side you see same different task, faster for very different things and for very similar things. And on the right side you see name a difference task, and it's faster for very similar things than for very different things. So it's an interesting dissociation. Basically, alignability makes differences pop out. So can we use this to teach in children's learning? And Rishua Shao and I returned to a classic finding in language acquisition, which is called fast mappings. This is a very beautiful study done by Carey and Bartlett a long time ago, Susan Carey and Elsa Bartlett. What they did was they wanted to see if kids could pick up a new word meaning from a very kind of casual comment. So they showed the child 2 trays that were identical, except one is red and the other is a sort of strange green color. And the teacher says, bring me the chromium one, not the red one. Now the children don't know what chromium means, right? They've never heard this as a color word. It's a new word. But bring me the chromium one, not the red one. The children very often would go bring the strange green one, and they maybe could have done that just by paying attention to not the red one, but some of the children were later able to pick out a new chromium object, even when it was quite a long time later, and different kinds of objects. So some of them had actually managed to learn what chromium means from this very casual remark. And what's impressive about this is no one ever pointed and said, that's chromium, right? The child had to pull it out of this rather indirect reference. So we suspected that the way the children succeeded, the way they figured out what chromium meant, was by aligning the trays, because the trays were identical in every way except color, which means they align very quickly, color pops out, and even a young child, a 3 or 4-year-old, is able to sort of notice this chromium as different from red. So how do we test this? Well, vary the alignability of the pairs. So what Rishua Shao and I did is we ran 2 groups of 3-year-olds and also 4-year-olds. One group gets a high alignability pair, like the Carey and Bartlett pair. The other gets a similar pair, except low alignability. Now, this is still would be pretty easy for you, but for a 3-year-old or a 4-year-old, we're guessing this is going to be quite hard, because they won't have the perceptual support of perfect alignability. So we use the same kind of idea. We say, pick out the chromium one, not the blue one. And the children, by the way, all get the right one. It's not, we say, show me the chromium one, not the blue one. They all point to the funny green color. So they can do that, but did they really get what chromium means, or did they just kind of pick the one that wasn't blue, which is what we, that is clearly one possibility. Well, the way we test that is about 5 or 6 minutes later, after a few other tasks, we give them 8 new objects, and they're all different colors. These are all little solid figures. 3 of them are chromium, and for each child, there will be 2 new ones and the one that they saw before. So we ask, can they generalize this word to new items? And what you find is that the alignable group does much better than the non-alignable group, both at 3 and 4. So the red bars there are the high alignment group. They got the identical objects except for color. And the blue bars are the low alignment group. What you see at 3-year-old is that only the high alignment group is above chance in picking out the 3 new items. The low alignment group simply doesn't get it. The 4-year-olds, actually the same is true. They're above chance if they got a high alignment pair. Otherwise, they really don't know how to retain chromium. They can't even pick out the initial chromium item. That is, even to pick out the one they saw before, high alignment group does better than low alignment. So this kind of perceptual alignment is supporting language learning in ways that I think parents and teachers may not be completely aware of. There's a sort of very nice interaction between aligning things, the perceptual structure of items, and figuring out what words mean. So we applied the same idea in a much more ambitious study in the Children's Museum in Chicago. And here we're going to teach an engineering principle. So we entered the Children's Museum because they had a problem with one of their exhibitions. This is an activity in which kids get to build a skyscraper with their parents. They're given some construction materials and they're told to build a tall building. And what happens is the children build a tall building and then it collapses, which is very disappointing. Now, why do they collapse? Well, because the children are missing a key principle. They want to build their buildings out of nice horizontal and vertical pieces, and they keep building up. But what they don't recognize is, if you look at that the middle part of the diagram, if you do that, then when you push the building, it will basically fall over. So they need to grasp that if you put a diagonal in so that you make more triangles, you will have a stable building. So here's how we teach them. Again, we're going to use this alignability idea. So we have a high alignability group and a low alignability group. And I'm just going to show you on the right side there the script that we use, but we say the same thing to the low alignable group. We show them two buildings. Notice one has a diagonal, the other has a horizontal instead. We say, which one do you think is stronger? And children are about 50-50. Then we say, okay, wiggle them. Let's see which is stronger. And when you wiggle them, you will see that you can't, the one with the diagonal is hard to wiggle. But the one that does not have a diagonal will bend all the way down to the ground. So after that, we say, now which do you think is stronger? And the kid says, they all get it right now. They all understand that the one with the diagonal is stronger. So, great. So now that's all we do. We don't give them any further instruction. They've seen this for themselves. So now there are three groups, high alignable, low alignable, and one group that got no training. They're 6, 7, and 8 years old. And we now send them in to do the fun skyscraper construction with their families. And then we find that the kids who we videotaped everything, and the kids who got the training are more likely to put in a diagonal, so that's great. But in that task, they're interacting with their parents. It's kind of complicated. So we wanted to have one task in which we got the child by themselves. So at the very end of the study, we take the child aside and we show them a building, and we say, this building is wobbly. Will you put this piece in and show me where to make it stronger? So we hand the child a piece, and the child holds it up. Now, the child can hold it up diagonally, or vertically, or horizontally, and we just record it. And that's our second piece of data. And what you find is that if the child has been in the comparison condition, they are more likely to put in a diagonal. So to take you through this graph, you see 6, 7, and 8, the ages, and the yellow bar is the children who got no training. And as you see, they're terrible. Even at 8 years old, they're not above chance. Kids really like horizontals and verticals. You know, that just looks right to them. But the dark red bar is the ones who got high alignment. And as you see, they're doing really very well. Not so much at the early age. The early age is still a chance. But the 7s and especially the 8s are doing very well when they get high alignment. And the low alignment group, the kind of lavender group, is in between. So high alignment makes a huge difference. Having this perfect comparison where the difference comes to you is something that I think makes an enormous difference in whether kids are going to learn something from a demonstration or not. The implications are comparison could lead to learning. Structural alignment is essential. If you give them a comparison and they fail to align, like in the low alignment group, you might as well have saved your time. They have to be able to align it. If they can, then they'll find the right correspondences, and the abstraction will become clear, and the key difference may become clear. Now, you're not guaranteed, of course, but you at least are on the route to really teaching kids something they don't already know. So this kind of principle we've used in various other education studies to teach about geology, to teach about the structure of skeletons. And I want to suggest that Darwin may have used this principle in his tour around the Galapagos Island. So as he went from island to island, he noticed that the finches, which all look pretty much alike, so they're easy to compare, but he noticed that across different islands they have different thicknesses of beaks. Some have little tiny beaks, and some islands have finches with very thick, strong beaks. After he noticed that, he also began to notice that the seeds vary across the islands. Some seeds are very hard, some are tiny and soft, and this was correlated with the finches' beaks. And this sort of made him think maybe the finches have adapted to the environments on their islands, so the ones that have very hard seeds have developed very thick beaks. This was clearly an important beginning, one of many such trails he followed on the way to proposing the natural selection hypothesis. So we're almost at the end here, but I want to just give you one example of how completely natural it is to do this. I've stressed there are a lot of things kids don't know, and so they will often fail to see a relational alignment that an adult will see unless you make it very easy for them. But what I think is really important is that we are always doing this spontaneously, and kids especially give themselves opportunities to compare. We enjoy doing this. We like finding commonalities. So I would give you an example that contributed by Art Markman of his child. This is Lucas, and when he was 2, Lucas had a house that he could play with that had doors and keys, and you could open the doors with the keys. So on this particular day, his parents are sitting at the table drinking coffee, talking, he's kind of ignoring the child because he's having a good time, he's playing with the house. And then at some point, Art Markman noticed that Lucas was turning the house over, looking on the bottom, turning it around, looking on the other side, looking intently at the house. And after doing this for a while, he looks up at his parents and says, "Where white door?" Well, what was that about? What they realized was each key goes with a door that has the same color, but there's also a white key, and there's no white door, right? So the reason is that the white key is a master key. It opens all the doors. But of course, Lucas didn't know that. What he did was he did this little 2-year-old analogy. Red door goes with red key. Red key goes with red door, green key, green door, white key, and then he has an inference, and he persists in trying to find that inference on his own until he finally asks for help. I think this is going on all the time. This is part of the invisible learning that makes us think that children start with all kinds of structures that maybe we don't need to suppose, because really we have these powerful learning processes that are sort of curiosity engendering, that give us inferences that make us seek more knowledge. So I think this is a microcosm of what is going on all the time in children's learning, and maybe adult learning too. So one example of where this might apply is in the kinds of overgeneralizations that we see when children are learning language. Melissa Bowerman did beautiful work on this, and she noticed that at a certain age, kids start saying things like, "Will you unopen this?" Now, this is not an English word. He tippy-toed to the graveyard and unburied her. This is also not an English word. Unburied is right. But the child has come up with this, right? Why? Well, what Bowerman suggests is that the child first, just like the red key, red door, white, green key, green door, the child learns a bunch of correct things. You can say unhook, untie, unlock, and it means sort of reverse. It means do the reverse of something, right? Roughly. Well, after they compare a few of these, first they use them correctly, but then they start comparing, these little active processes start going, and it leads them to think, okay, got it. I mean, not overtly, but they just find themselves trying it out on other items that in fact adults would not apply that particular morphology to. So now you get unbury, and at one point another child said, "I hate you, and I'll never unhate you again." Right? Another non-English way of talking. So, summary. I want to suggest that structure mapping is central in higher order cognition, that the same processes operate in children and adults, different levels of knowledge, but the same processes, and that they enter into a large array of cognitive processes. And I'll just end with this comment by William James. The faculty for perceiving analogies is the best indication of genius. And what I want to suggest is, by that criterion, we are all geniuses. Thank you.
So we have time for questions, and I'll bring the microphone to you when you raise your hand. If you raise your hand.
Deidre, thank you. That was a wonderful talk. I'm curious to hear you speculate about the relationship between the evolution of analogy making and the evolution of language.
That is a great question. Well, yes, I have thought about that. Speculatively, I think it's possible that what really drove analogy, our analogical ability, is in fact language. That when we analogy people speculate about why humans are so much better at this than chimpanzees and other apes, why we're such paragons. People think about things like tool making. It would be handy. Maybe the evolution of our analogical cognition was developed by tool making. I think it could have been language, because if you're a Neanderthal or a Cro-Magnon person, and you begin to, or it would have been actually previous to this, but you begin to be able to talk about objects, and say elk, meaning let's go hunt it. That's fine. But if you can begin to say, you take the head and I'll take the heels, or you go up ahead and hide like we did for the other animal we hunted, you have a whole different situation. I think that learning language requires analogical processing. Really, syntax is just a whole bunch of analogical structures that then become, could be seen as just a whole bunch of analogical structures that then become abstracted into a relatively abstract grammar. And as you know, it's not a totally, even abstract grammar is not as abstract on some accounts as we used to think it is. Anyway, my speculation is that actually analogy and language drove each other, and that the skills you need to learn grammar turn out to be useful for learning mathematics and science and developing better tools and all the rest of the incredible things that we do as a species. So yeah, I do think they might be related. I'd be curious about your views on that, Barbara.
Any other questions?
Thank you, for me as well. I was wondering to which extent your research already has made it into informing curricula, for example, for kindergarten. Kindergarten in the US is when they're 5. In Europe, I think it's when they're little, so the terminological confusion. But like preschool, is that one direction in which you're seeing your research going?
Thank you. That's a great question, Alexei. Yes, I strongly would guess that these methods could be really powerful for preschoolers and kindergartners. Some of these techniques are being used by people at the University of Chicago in connection with a group that's called Early Mathematics. What is it? Everyday Math, right, that makes workbooks that are used in many schools. And, I think there's evidence not just from my work, but for example from Mix's work, right, on that when you show closely aligned examples of mathematical concepts, even simple concepts like how many are there, kids will do better if they're easy to align. So I think this could be a much more powerful principle than we currently realize in getting early learning off the ground.
Yes, thank you very much for this talk. I was interested in this early example about teaching the word Toma. Now you see, I mean, from a child's perspective, the question is, what to find out. You don't know. I mean, so you said that early there is an objectual bias, and later there's a relational bias. But still, that is to be explained, and I mean, as we know, many language concepts are not exclusively one or the other. So what happens?
Yeah, you're absolutely right. And I actually would not argue that that we adults are solely focused on relations. I mean, objects are important, right? I would not want to confuse this with a microphone, for example. No, objects always remain important, and we've done studies even with adults. If you if you're asking them to do a relational task, but you put in a incorrect object match, the adult will be slower. You know, we adults we're pretty powerful, you know, focused individuals. We can pay attention to relations even when they're competing objects, but it's hard. You know, objects matter. No, I don't think we ever stop paying attention to objects, but what does happen is we become able to focus on relations, and that's partly because we have a lot of relational representations that, you know, you can grasp very quickly. When an adult learns a completely new topic, for example, when you look at beginning physics students, they look just like kids. Mickey Chi has done some studies where she takes beginning physics students and she says, sort out these physics problems and put the ones that go together, you know, in the same pile. And a beginning student ignores ideas like momentum and energy and force. They put all the ones that have, you know, a pulley in one pile, and they put all the ones that have sort of what looks like an inclined plane, a seesaw, in another pile. Basically, they sort by objects. They look like our 3-year-olds. And so what I think is going on is if you know the relations, then you can apply these powerful processes. If you have no understanding of the relations, then you'll attend to objects. And it's the same with adults as with kids. Somehow, I'm having trouble hearing.
Hello.
Wow. No, wait, it got soft again. Sorry.
Hello. I'm sorry. Have you heard about the Marie Montessori method?
Oh, I see, yeah. You're asking how would this relate to the kind of thing that Montessori does?
Material.
So that she's using, her system uses some of these same ideas? Is that what you're, yeah. You know, thank you for pointing that out. I believe you're probably right, and honestly, I have not looked closely at Montessori's method, but what I've seen leads me to believe that you're right, that she recognized some of these ideas maybe, and so I thank you for reminding me. I would like to look into that more. Oh, sorry, yeah, I got everything but the word creativity. You know, so there's two parts to that's a great question. I think it's two great questions at least, maybe more. Let me answer the easier one first, the one I think is easier. Is there a relation between this kind of ability and creativity? Absolutely, I believe. I think there are many contributions to creativity, and you know, artistic ability and scientific ability are not 100% the same, but I think they're partly the same. And that part of what I think a great creator does is they take analogies seriously. They love them. They play with them. I'll use Kepler as an example. I've read a lot of his journals, and one of the sort of charming things about Kepler's writing is that he explored many analogies. He was trying to explain in the year 1600, 1620, before there was any good model of the solar system, he was trying to understand how it was that the sun could attract the planets and keep them moving around in sort of these elliptical orbits that he worked out. Well, he used all kinds of analogies. He had the planets as boatmen riding in a current that the sun created, and then he had the sun as magnet, and the planet, the planets as iron filings, and magnetism had just been discovered, and so on. He tried analogy after analogy. He had an analogy between gravity and light. He was making up this force from the sun to the planet, and he said, how could there be a force that you don't see? How could there be action at a distance? And he said, well, maybe it's like light. If you have a light, in between the light and the object, you don't see it, but then it illuminates the object. Maybe this force from the sun is like light. Then he pushed that and said, well, what about an eclipse? Do we see an eclipse of the gravitational force? He didn't call it gravity, but anyway, he took them really seriously and pushed them. And I think that part of what that does is it gives you many inferences to explore. Like that kid who looked for the white key, the white door, only in, many times more. And it makes you go deeper. And it also, because you explore that relational structure a lot, it becomes quite memorable. It becomes something you can retrieve again later. There's I didn't talk about this, but one of the major blocks to getting good ideas from analogy is we don't think of the right analogy at the right time. And I think the more you play with analogies, the more you think about the common structure between two unlike things, the more you make it accessible later. It becomes part of your internal vocabulary that you can draw on. So I think there's a very strong relation between analogical habits, let's say, and creativity. And it's partly being an active analogizer, not just being born brilliant, but being born curious. I think that helps make people creative. But I think you asked a second question, which is, I think, how do you get a new relation if you don't already have it? Yeah, that's a really hard one. That's sort of Fodor's question. Taken to the extreme, you may know that Fodor has this challenge to all of us who believe in learning, and it goes like this. In order to learn something, you have to be able to hypothesize it. But if you can hypothesize it, then you already know it. So really, nothing new can be learned. Therefore, this forces Fodor to propose that the concept of telephone, for example, is innate. So it's when this conundrum is proposed, of course, you say, well, wait a minute, that can't be right. But it's not so easy to argue against it. How do you, if people are, children are comparing two things, and let's take the pigs and the goldfish, they didn't see the relation of symmetry in either one of them. How is it going to come out of comparing them, right? I'll give you my best answer. I will acknowledge that I don't have all the answers for that, but I think that partly we have many relations that we sort of, there are two parts to it. One is sometimes I think we see fragments, partial relations. When you put the thing together, it makes a more complete relational representation, and then it emerges. That's hypothesis one. Hypothesis two, these could both be correct, is that we see many relations in a very implicit, context-specific way. So this one I actually have more confidence in. When the child sees the two goldfish, for example, they might sort of say, they're kissing, right? Then they see the two pigs, and they might be thinking something like they're talking. And the idea that they're facing each other, that they're symmetric, is not really it's very contextually embedded. But when they put them together, it's a little bit like Walcorp divesting Best Tires and Martha divorcing George. Divest and divorce are very different, but you put them together and you look for the commonality, which is get rid of. I think it might be that kissing and talking, facing each other, could, when you put them together, that there's this, we like finding commonalities, and that the desire to see what's alike implicit desire, not a conscious desire, but this implicit desire pushes it to becoming something more like symmetric. I mean, I'm sure the kid doesn't have a fully abstract idea of symmetry, but maybe something like animals facing each other, something like that. Anyway, I think context-specific relations may become more general. That's one way in which I think something new could emerge when part of it is already there. But clearly, there are limits to this, right? If you don't have any raw material, you're not going to discover general relativity just by comparing two things. So you have to have some inkling of the relation before it will emerge. Sorry to take so long, but that's a great question.
So just a couple of logistical remarks. We are having the parallel sessions now, and they will take place in